Hi, welcome to the second lecture for Coursera's Instrumental Analysis. This is really a chemistry review lecture, so if you did well on the quiz, this may be a little bit overkill for you, but feel free to watch. It'll be fairly quick. We're going to talk about units used in calculations, the concept of dimensional analysis, and a couple of examples of applying it. So dimensional analysis is really going from one unit to another. It's if you have, for example, 12 apples, you got 1 dozen. But how mathematically can we formalize that? You can do it in your head for simple things, but what if there's a lot of units involved? Where it might be a complicated calculation, you need kind of a system for saying, okay, I know I have one piece of data or one measurement. How do I put it in another unit? And I'll just point out that units are as important as the number in any measurement. Often machines will spit out a number, but if you don't know the units, is it apples or is it a dozen apples? Is it pounds or is it kilograms? Then effectively the information that you've measured is useless. So it's a really foundational principle in instrumental analysis. Okay, so what we're going to do now is we're going to do a little bit of problem solving. So I'm going to zoom in and show you how to do, not in your head, but in a formal way, the problem. If you have 72 apples, how many dozen do you have? Okay, so to do this, you first need to know the conversion. We know that 12 apples is equal to 1 dozen. And that's going to be called basically a conversion. And as we do dimensional analysis, knowing your conversions is going to be really, really important. So you take 72 apples and you want to multiply it by a number that doesn't actually change its value, but it changes the units. And what that's going to be is it's going to be the conversion, but it's going to be the conversion written as a fraction with 12 apples on the bottom and 1 dozen on top. Now, if you think about it, you can say, since 12 apples is equal to 1 dozen, this whole thing is equal to 1. So when you multiply this out, you're just multiplying the 72 apples by 1. You haven't really changed anything about it. And what you get when you do that calculation is you're going to find that it's equal to 6 dozen. And I think the other thing important to point out is that we knew to put the apples on the bottom because the other feature of dimensional analysis, besides multiplying by a 1, is that you cancel the units. If it appears on the top and the bottom, they go away. And that's how you know you're left with a dozen. So that's a basic idea then in a dimensional analysis. We're going to put down the information we're given. We're going to multiply it by maybe one conversion factor or several, using the fact that the conversion factors equal 1 and that the units have to cancel. And that way we can go from kilograms to grams, liters to milliliters, or one of the many concentration units we're going to care about in this class. Now, conversions are really essential information for an analysis. You have to know how many milliliters are in a liter, for example. And so those conversions are ways in which you take one form of units and put them into another. Okay, so let's do a couple of examples. Okay, let's start with this. You always write down your given. If you don't know anything else to do, write down your given. So there's my given. And we know this to be the case because the problem tells us this. So this is writing your given, and that's step 1. Now we're going to have to multiply it by a conversion factor. And this is where you have to remember what the conversion between kilograms and grams is. Now right now I wrote kg because I expect that you would know that a kg is a kilogram, but I'll write it out here just to be explicit. Kilogram and kg are the same. So how many grams are in a kilogram? Well, that's 1,000. So you're going to multiply all that out, and you're going to get an answer, which is 34.5 times 1,000. Now, we like to use scientific notation when we're reporting answers, so this is the best way to write it. So as you can see, we're canceling units, writing the given, and converting from kilograms to grams in a really structured way. Let's go on to the next example. You have 1 quart of milk. We're going to write down the given. Okay, what's our conversion? Well, I had to look this up on Google, actually. I did not know it. And it turns out that 1 quart is 946 mil. So when you have a sentence like that, 1 quart is 946 mils, you can write it as a conversion. And so when you do that, you get 946 mils of milk. Again, canceling our units, and again, writing our given. So as you can see in these two quick examples, there's some themes. You write your given down, whatever the problem gives you to start with, and then you multiply it by conversion in which the units that you start with are on the bottom of the conversion factor, so you can cancel them and then end up with the units you want on the other side. So this time I'm going to be assuming that you know something about what the molecular weight is of a substance, and that's what you're going to see in these examples. So we're starting out as we did before with 34.5 kilograms of sodium sulfate. The problem is I'm now asking for moles, and that means you need molecular weight. So just to review, to get the molecular weight, you're going to sum all of the atomic weights that go into the molecular formula, and you're going to weight them by how many atoms are present. So sodium sulfate, as you saw in the last example, is Na2SO4. So there's 2 sodiums, 1 sulfur, and 4 oxygens. We look up the atomic weight on a periodic table. It's usually given right under the letter, and we multiply those out, sum them to get a total molecular weight for sodium sulfate of 142 grams per mole. So what we're going to do then next is we're going to start by writing the given, which is 34.5 kilograms of sodium sulfate. Now we need to go from kilograms to grams because molecular weight, as you can see, is always in terms of grams. And then we're going to multiply by the molecular weight. Molecular weight means that 142 grams is equal to a mole. Whenever you have one thing equal to another, you can write them as a fraction, and if the thing on the top is equal to the thing on the bottom, the fraction is 1, and you have a conversion. So as you can see in this example, we have a new example of a conversion factor, which is in fact our molecular weight. So we do that calculation, we can find 243 moles of sodium sulfate. Okay, why don't we start the next one? So the first thing you have to know is what aluminum nitrate is. This is a little bit of a test. Aluminum has a +3, nitrate is a -1, so you have to know how to write that formula. Here's the molecular weight calculated as I did before. We start off by writing our given, and then again we multiply. Now this time we're given moles, so now moles goes on the bottom so it can cancel to leave us with grams, and then eventually to kilograms. So in these two examples you see a lot of the same features as we had before. First off, you see, starting with the given, the other thing you see that's important is the canceling of units. Moles in one case, kilograms in another. Here we go with a second conversion. And you can also see that you can actually stack one conversion on top of another, and you can put them in series to get your answer, which is what you're going to be doing most frequently when you do this kind of analysis. So I hope this brief lecture has given you some ideas about how to do dimensional analysis. It's a formal way of converting units, and when you're doing pretty complicated chemistry calculations, relying on dimensional analysis can be a surefire way to always have the right answers and in the right units. Thanks so much, and see you next time.